In this lesson, we're going to talk about solid figures such as the prism and the pyramid. First of all, they are the family of polyhedrons, so we need to define these, first of all, so we know what we're talking about. Officially, technically, a polyhedron is a geometric figure made up of a finite number of polygons that are joined by pairs along their sides and that enclose a finite portion of space. In short, then, this is an example of a polyhedron. It's a many-sided figure that encloses a portion of space, and these two consecutive faces are joined by pairs at two at a time and enclose this portion here. Here's another example of a polyhedron. And we have others, like this, and it matches the definition we're talking about. This is also a polyhedron. So it's kind of a general name for prisms as well as pyramids. A prism, then, is a special kind of polyhedron. It is a polyhedron with two congruent faces contained in parallel planes. Now think about that a minute. Two congruent faces are in parallel planes, and its other faces are parallelograms. This is an example of a prism. That matches the definition. Again, it says two of the faces are congruent. That would be this face and this face. These are congruent faces there, this side and this side. They are formed by the intersection of parallel planes, slicing here and underneath here. The other faces are actually some type of parallelogram. It might be a rectangle like this is, or it could be squashed over and be a parallelogram such as this. If it's squashed over like this, then it would be what's called an oblique prism. Straight line there. So if the faces would be parallelograms like this, then we get this oblique prism. So the height of that, you see, would be out here in the exterior, perpendicular to this plane of the base. So that's what's called an oblique prism. This is the more popular type, however. This is the ones we'll mainly be dealing with. This is called a right prism, because all of these faces are rectangles, and they are perpendicular mainly. They are perpendicular to these two bases. So we're talking about right prisms. This is a right hexagonal prism because the two parallel faces are hexagons. The other faces around here are rectangles. Now, there are some terms that we need to clarify about this prism. The parts of this prism are defined like this. The bases, as I said, are the two parts here that are cut by the parallel planes. The yellow sides here and here. Those are the bases. The altitude of this thing would be from the top face perpendicular to the bottom face. Or in this case, to the bottom face extended. That would still be an altitude. It always has to be perpendicular to the base. But in this case, being a right prism, the altitude would be perpendicular right down straight through the middle, right through the axis of the thing, like this. Or it could be the same as a measurement on any of the sides. That would be also the same measurement as an altitude. These red segments, or sides, these red sides are lateral faces. Lateral faces, meaning the side of the thing. So if we're talking about lateral area later on, we would just be talking about the area of these red faces around here. Just the area of the lateral sides around here. That's lateral area, not including the base, top and bottom. Then if you want to talk about total area, then you would go ahead and add on the top and the bottom bases. Now, in a right prism, the top and the bottom bases like this should be congruent. And these then would be, of course, rectangles coming down as special parallelograms. So we have lateral faces. We have lateral edges coming down here and there. Where two lateral faces meet would be a lateral edge. And then you have a base edge going around this, where a base intersects with a lateral face. So the lateral area would be the red sides all added together. The total area would be adding on the top and the bottom to the lateral area. And then, of course, it has volume as well. And we're going to talk about some of those relationships today about a prism, a right prism primarily. And let's look at some of the things about it. For any rectangular solid, this is one of the simplest of all prisms. Nothing more than a box. a rectangular solid. Now, this polyhedron here is actually a prism which is oblique. It's like this box got squashed with weight or something. So its altitude, you see, would be out here in the exterior. So this is an oblique rectangular solid. But again, mainly we'll be dealing with these right rectangular solids. They're more common anyway. They're more fun to deal with. So for any rectangular solid, the volume equals the product of its length, width, and height. Now, the three edges, where they come together, those would be your length, width, and height. And you know what? It doesn't matter, luckily, which one you establish as length, which one is the width, and which one is height. As long as you choose the three dimensions of three edges that come together at a vertex, that would be enough. If you turn this thing up on edge, then you might say, well, now that changes this to be the length, and then that would be the width, and this would be the height. You know, it depends upon how you turn the box around. So it doesn't really matter. Volume, again, is length times width times height. Let's take a look at an example of that. Let's take a common shoe box. And again, it's not drawn to scale, so just accept it as it is. We'll call that a shoe box. And let's say this dimension is about 14 inches long, and it's about 8 inches wide, and about 6 inches tall. All right? And again, either way you rotate that box, these are the three dimensions that come together at a vertex. So those are the three that you would use. The volume of this is its length times its width times its height. And in any particular order, it doesn't matter, because when you multiply, you can multiply in any order you want to by the commutative properties. So let's say 14 times 8 times 6 inches times inches times inches. And when you multiply those three numbers together, you get a total of 672, what type of label? Inches times inches times inches would give us cubic inches. Cubic inches. All right, so that's the formula for the volume of a rectangular solid. Let's look next at a right prism. The lateral area, sometimes abbreviated then LA, of a right prism equals the perimeter of a base times the height of the prism. The perimeter of the base times the height of the prism. Now, these formulas I'm going to show you today don't just happen. They don't just come about by happenstance. They are logically derived from rectangles or parallelograms and things like this. So it's very commonsensical if you think about it. There's really nothing you should have to memorize, but rather understand. All right, let's draw a picture of that. A right prism would be like this model I showed you here at the top of the show. So again, let's say we have this right prism. I can draw this again real quickly. And parallel to this other face down here. And connect the corresponding vertices. And it's perfect. Okay, so the lateral area, remember that would be just the area around these sides. Just, in this case, the red sides. See what a perfect match that is? Just the lateral area would be just the red sides, not including the bases. So the lateral area, it says, is equal to the perimeter times the height. Well, look all what that is. That is simply a series of rectangles. That's all it is. You could find the area, of one rectangle and then multiply it times how many rectangles you have. So instead of, base times height and then times the number of sides, the perimeter takes care of it. The perimeter takes care of all of those bases all together. No matter how many sides you have, see? These bases could have, 3 sides. It could have 4, 5, 6, 7, 8, any number of sides. They don't have to have just 6 only. So the perimeter would be like a series of all the bases times all their respective heights. Okay? So that's how this comes about. It's simply the sum of all of the bases along here to make the perimeter. Let's say this is 4 and this is 8 up here. The lateral area, therefore, would equal its perimeter. If one edge along the base is 4 and you have 6 of those base edges, then the perimeter would be 24 all the way around there. So the perimeter is 4 inches times 6 sides. And then the height of this thing is 8. Okay? So again, if you're not into memorizing formulas, then just understand how the formula comes about. It's just a matter of adding the areas of all those rectangles around there. All right, so multiplying this on out, 4 times 6 times 8 would be 192 square inches. Don't forget, we're talking about area now. Lateral area or total area always would have a unit in terms of square units, square inches. Okay, how about the total area of a right prism? The total area naturally would just add on the top and the bottom sides, you know, the two bases. So the total area is the sum of the lateral area that we just found, and then let's add on the area of the two bases. Very simply. TA equals the lateral area plus 2B. Okay? So again, let's go back to the same drawing right here and find the total area. We already have computed the lateral area, so to save time, let's just add on the area of the bases. Well, how are you going to find the area of this base? It is a regular polygon looking like this. It's a regular hexagon. All sides are equal in measure, and all angles are equal in measure. If I take this base out of here, this base is what I have redrawn up here right now. Okay, and look what I have been given to work with here. This edge is 4. Okay, so what I have to do is define the area of this base. And once I do that, then I can double it. So again, total area, let's write down the formula first of all so we know what we're going after so we can stay focused, is the lateral area, which is just the sum of those rectangles plus the area of this doubled. So the lateral area we've already computed to be 192. That just kind of plugs in and comes along for the ride. It's waiting now to find the area of this base. Okay, to find the area of any regular polygon, the area of a polygon, recall from a previous lesson, is 1/2 its apothem times its perimeter. A theorem or a property we just learned in the previous lesson. So 1/2 the apothem. The apothem, remember, is like the radius of the invisible inscribed circle, or therefore the apothem comes from the center of the polygon perpendicular to the side at its midpoint. So that would create a right triangle in here. And because this is a regular hexagon altogether, each central angle in there is 60, and this then bisects that angle. What we have right here, therefore, is an equilateral triangle. If it were not one of those special right triangles, we'd have to use trigonometry with the measure of an angle and then compute the measure of the apothem that way. But let's make it easier for ourselves. That's why I chose this hexagon this time. This would become then a 30-60 right triangle then on each side, right here and right there. So this 4 then divides up into 2 and 2. Let's pull that right triangle out of there so we got a little bit more room to work. And this right here then becomes, cheap chalk. And the apothem is what we have to find right here. Now this is a 30-60 right triangle. We decided that because of the nature of the part of it being a part of the hexagon. So in a 30-60 right triangle, recall, if you know the measure of the shorter leg going to the measure of the longer leg, you multiply times radical 3. So this would simply be then 2 times radical 3. Okay? The hypotenuse, if you wanted to find that, would be twice the measure of the short leg. But you really don't need that in this case, but there's a little extra bonus for you. There, the apothem is 2 radical 3. Let's plug that back up here where we need it. The apothem is 2 radical 3. We needed that for the area of the whole polygon. And the perimeter of it would be 6 times the measure of a side. 6 times 4 would be 24. So the area would be 1/2 times this times radical 3 times 24. So that would be 24 radical 3, since those would cancel out. And that would multiply out to be 48 radical 3. All right? So we add that on down here. And we have to double it, because that's just the area of one base. See the error you might make? Don't forget to double it. 2b, it says, or not to be. So don't forget to multiply it times 2. And I made a mistake up here. I'm sorry. This is 24. Got ahead of myself. This is 24 radical 3. And so the double of that, one base, would be 48 radical 3. Now we're back on track. Always double check yourself. That is a common careless mistake we can make, is forgetting to double the base or doubling it ahead of time before we should. All right, cranking this out into a decimal. If you multiplied radical 3 times 48 and then added on 192, you would finally get 275.14. And again, this is total area, so it's square units. We'll say inches here if we start out with inches. Okay? So it's simply the lateral area, all the faces around there, plus the area of the top and the bottom sides. Total area for a right prism. How about the volume of a right prism? Let's use the very same drawing again. The volume of a right prism equals the area of the base times the height of the prism. Okay, another new formula to memorize, you say. But again, it's common sense. Think about it. We're trying to find the volume of this thing now. We're going to try to fill it up. Okay, volume means the whole quantity that it contains. Well, think of the area of this whole base as a solid area, solid figure right here, solid plane figure. Not hollow, but solid. And then you multiply that times the height. So it's like you're taking this base and multiplying it times the height, just like an elevator. And that elevator would fill up all the way up through the shaft, see? And that would complete the volume of the whole shaft. So it's the area of the base times the height of it. So it's a natural, logical formula to use. So let's use this same figure right here and figure its volume. The volume of this thing, let me erase this so I get some area to work with right in here. The volume of this thing is the area of its base times its height. Now the area of the base we just computed over here. Luckily we correct our mistakes because we've got to use it again to find the volume. The area of the base was the area of that hexagon, 24 radical 3. And the height of it is 8. Okay? You understand how that would be then? Just the area of the base solidly and then just fills it right up like an elevator. So you multiply this all the way through and you can change it into a decimal if you like, and the volume turns out to be 332.55, and that's volume, so it's cubic inches. Okay? Volume because you have in the base you have inches times inches, and in the height then you have another variable of inches, so it's inches cubed. The volume of a cube with edge E is the cube of E. How tough can that be? The volume of a cube with an edge E is the cube of E. So this is like another rectangular solid. It's a special kind of rectangular solid. So if you go back to that shoebox application and change that shoebox into a cube so that all three dimensions are the same, then it becomes just that. From a rectangular solid like this, if you change all the dimensions so they're all three the same, then it changes into a cube like this. Okay, it's a 3D drawing here if you can visualize that. Going back in here. Perfect. All right, so if we know the measurement of just one edge, E standing for edge here, that would be enough to find, you know, the volume of this cube. Let's say the edge of this cube is 12 inches. Well, if that's 12 inches, then this is 12 inches, and so is this 12 inches. So it's like the old volume formula for the area or the volume of a rectangular solid, 12 times 12 times 12, though. So we can shorten it to be then just E cubed, which would be 12 cubed, which would be 12 times 12 times 12, which is 1,728 cubic inches. That would be the volume of this cube that was 12 inches on an edge. Now think about that. There's something more there. If that's 12 inches on an edge, that means it's 1 foot on an edge. 12 inches being 1 foot, isn't this 1 cubic foot? 1 foot by 1 foot by 1 foot. So in 1 cubic foot, there are 1,728 cubic inches. All right. Let's talk about pyramids next. A pyramid looks like this. You can recall the definition, but in general it looks like this. We have one base, and then all these other lateral faces all come to a vertex. This is a pyramid. Okay? The parts of the pyramid we have, as I said, the base. Down here we have one base this time instead of having two bases as in the prism. So it has one base. The altitude would go from the vertex to the middle of the base, just like this, perpendicular. Just like, you know, between fingertip to fingertip. Now, it is possible, again, for this to be slanted over to one side, and that would make it what's called an oblique pyramid. Let's see if I can draw that real quickly. We've got the base would be, a hexagon, and we had a vertex over here like this, slanted. The height of it would still maybe be perpendicular to the base extended out here, but again, you can see it would be like this thing only squashed over. So that would be called an oblique pyramid. But again, the more we work with these are the easier ones to calculate, to find the areas of and the volume. These are the more common ones because they're prettier, they're more symmetrical. So this is a right pyramid. Now again, the altitude goes from my fingertip to fingertip, perpendicular to the base, and we have lateral faces around here, and we have the base face, and then we have lateral edges coming down where the two consecutive lateral faces intersect, and again you have base edges along here where the base intersects a lateral face. Okay, this is called the vertex, just like in an isosceles triangle. You have the vertex at the top, all the sides coming down being equal, and again, that's the vertex up here on the top then. Now, this is the lateral area. Total area would be this lateral area plus the area of the base, and then, of course, once again, you have the volume of this. Now, how do you think the volume of this compares to the volume of this prism? How does the volume of this pyramid, do you think, compare to the volume of this prism? The bases are the same. That is the same dimension as this. They're both the same size hexagons. The heights are the same. They're both measured to be 8 inches. Both heights are the same. But how do you suppose their volumes compare? And maybe their areas, surface areas compare, when all these sides taper into a point like this? Something interesting to find out. I wonder how that would work if you tapered all those in, came to a point. Well, we're going to see here in a minute. Okay. Get through some other formulas here. The lateral area of a regular pyramid equals 1/2 the product of the slant height and the perimeter of the base. 1/2 the product of the slant height times the perimeter of the base. Okay, again, let's draw this regular pyramid. And it's a right pyramid, so we want this altitude going right down perfectly like that. It's in behind, comes on there, lateral edge, lateral edge, lateral edge, right in behind. All right, let's bring this over just a little bit so we can see it where it comes down there. Okay, now the lateral area, it says, is equal to 1/2 the slanted height times the perimeter. Now, the height of this original prism slants over and now becomes slanted. That's why they call it L. This is called the slant height. S-L-A-N-T-H-E-I-G-H-T. The slant height is L. So the slant height would be right down there in the middle of a side. That's the slanted height. So it still can be used in finding the lateral area because it is actually the height still of that triangle, isn't it? So it's just like nothing more than the base of this times its height. And then that's the area of one triangle, its base times its height, times 1/2 that is, and then times however many how many triangles you have altogether. So that takes care of the perimeter, you see. Adding all these bases together would take care of your perimeter. And the L, slanted height, is your height of each of your triangles. So again, it's a very logical formula which evolves from the area of a triangle and then duplicated. Now, total area, what do you suppose that might be then? Logically, lateral area plus what? One base. So if you found the lateral area of this thing, find the area of the base one time and add it all together. Simple enough. The total area of a regular pyramid equals the lateral area plus the area of the base. We already figured that out. The volume of a pyramid is 1/3 the product of its height and the area of its base. That gets back to something I mentioned a while ago. The volume of a pyramid is 1/3 the product of its height and the area of its base. Okay? Let's think about that a minute. The volume of this pyramid is 1/3 of the area of the base times its height. Remember I said these two have the same bases, so the areas of the bases would compare 1 to 1. They'd be the same, and they also have the same heights. They're both 8 inches in height. But by tapering in these sides of this thing to make a pyramid like this to a point, it's not just half, but rather 1/3 now. So if I were to fill this up with water, let's turn it upside down and cut it out and fill it up with water, make a cone out of it, if you will. If I fill this up with water, how many times would it take me to fill up this prism? 1, 2, 3. Because this is 1/3 of this, of course. All right? Now, let's compare the lateral areas, total areas, and the volumes of these two objects. The prism, the pyramid, and their areas and volumes. You can see when it boils down to, as we try to explain, into rectangles and triangles, that some of them are very logical. The lateral area and the area of the bases are nothing more than finding the areas of rectangles, triangles, and regular polygons. Here is the main comparison we were just trying to emphasize. How does the volume of a prism compare to the volume of a pyramid? Assuming they have the same bases in area and the same heights in measure, the pyramid would be 1/3 that of a prism. Okay? Now, I'd like to talk about this little rascal right here. Good. This is a pyramid kind of tucked away. If I bring this out, put that up on top of there, bring this out, there I've completed a nice pyramid. This is the same as this drawing right up here. How do you suppose the volumes of these things compare one to the other? Now, the base of this is 12 on the very bottom. And then I slice it up 1/3 of the way up, and this is 8 inches around the edge here. And then I come on up 1/3 of the way, or now 2/3 of the way up from the bottom, slice it again. Now this edge would be 4 inches on an edge. Okay, that's the way it would work. Again, I start out with 12 inches on a base edge. I come up 1/3 of the way, and it's 8 inches. 1/3 of the way more, it's 4 inches on an edge. Well, you see what that does to the areas of the squares in there? This is now, what, 16 to 64 to 144. Okay, just the area of the bases there, just the squares would be 16. This would be 64. This base edge would be 144. Look how those compare one to the other. And the heights, look how they compare. I made them, of course, cut symmetrically. So this would be 8. This height from here to here would be 16. And this height would be 24 altogether. Well, this height is 1/3 the height of the entire pyramid here. How do you suppose then the volume here? Just leave it with this answer, this question. How do you think the volume of this top pyramid would compare to the volume of the whole entire pyramid? And also, how do you think it would compare to the volume of the medium-sized pyramid? All symmetrically shaped and cut, like so. Well, if we applied the formulas here, if we took the time using these numbers, I want to show you some interesting numbers. The volume of the upper pyramid in here. The volume of the upper pyramid. Let's get these other numbers out of the way so we don't confuse ourselves. The volume of the upper pyramid would turn out to be, to make a long story short, 42 2/3 cubic units, of course. The volume of the middle pyramid, from here to there, would be 341 1/3 cubic inches. The volume of the whole entire pyramid, the whole thing, that volume would be, let's see if I find it, 1,152. Okay, now, again, I'm comparing the volumes of the upper pyramid with the one that's 2/3 of the way down with the one that's all the way down here, the total thing. Well, if you look here and compare, this times 8 is equal to the volume of this. In other words, This is only 1/8 of the area, or volume, I should say, of this pyramid here. Only 1/8. You wouldn't think it'd be that small by comparison, but it is. Well, what fractional part of the whole thing do you think this upper pyramid would be? This is the killer. What do you think the volume of that would do when you compared it to the volume of the whole thing using these symmetrical dimensions? In other words, how would this little thing right here compare to the whole thing together? Well, if I took 1152 and divided by this volume up here, it would go into it 27 times. 27. That's all because the edges of the sides or the bases are changing as well as the heights. You know, the heights are changing by 1/3 and the edges are changing by 1/3. So 1/3 and 1/3 by 1/3. You see that? The heights changed by 1/3. 1/3 of 24 is this 8. 1/3 of this side is 4. And 1/3 of that side is 4. So the change of 1/3 times 1/3 times 1/3 is 1/27. That explains these numbers. So there's a lot of logic here. Again, very commonsensible. There's nothing to be afraid of with these formulas. They look kind of scary and sophisticated, but it all just boils down to triangles, squares, rectangles, and regular polygons. In our next lesson, we're going to talk about cylinders and cones. And a lot of the new theorems and formulas there, terms, areas, volumes, lateral areas, total areas, a lot of brand new stuff. Really neat.